NASA has officially announced plans to forge a nuclear path to Mars, confirming that chemical rockets alone cannot get us there safely. The real stakes are simple physics. Without this shift, human crews face radiation exposure and life support failures during transit times of 6 months or longer. By the end of this explanation, you will understand why specific impulse is the single most critical number in spaceflight and how it forces a fundamental change from combustion to fission for any viable Mars mission. To grasp why chemical propulsion hits a hard wall, we need to look at a metric called specific impulse, often abbreviated as ISP. Think of this not as speed or thrust, but as fuel efficiency measured in seconds. It tells you how long 1 kilogram of propellant can produce enough force to lift itself against Earth's gravity for that many seconds. A standard chemical rocket engine typically achieves an ISP between 300 and 450 seconds. This means the engine burns its fuel relatively quickly compared to what is theoretically possible. The consequence of this limitation is a massive mass penalty where over 90% of the launch vehicle's total weight at liftoff must be propellant just to reach orbit, leaving very little room for anything else. When you apply these limits to a Mars mission, the numbers become insurmountable for human survival. A chemical-only trajectory requires 6 months or more of transit time through deep space. During that window, astronauts are exposed to cosmic radiation and solar particle events without any planetary magnetic field to shield them. Furthermore, keeping food fresh, recycling water perfectly, and managing psychological stressors over half a year creates engineering challenges that current life support systems struggle to solve reliably. The propulsion system becomes the bottleneck because it dictates how long you must stay alive in space before landing. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This is where nuclear thermal propulsion changes the entire equation by targeting an ISP of around 900 seconds. To visualize this, imagine your chemical engine as a short sprinter burning all its energy instantly, while the nuclear engine acts like a marathon runner maintaining a steady output for much longer. By doubling that specific impulse number, you theoretically cut the transit time in half to just 3 months. This reduction is not merely convenient, it transforms radiation exposure from a lethal probability into a manageable risk and makes life support systems far more viable with reduced mass requirements. However, achieving this gain requires overcoming severe engineering hurdles that do not exist for chemical rockets. The core challenge lies in thermal management inside the reactor itself. To reach those high specific impulse numbers, the propellant must be heated to temperatures exceeding 2000 Kelvin before being expelled through a nozzle. This creates a critical bottleneck where the reactor's operating temperature must be coupled with lightweight radiators that cannot be scaled linearly. You face a trade-off between power density and radiator mass that dictates the entire spacecraft architecture because you simply cannot dump heat fast enough without adding weight that negates your efficiency gains. The materials science required to handle this environment is equally unforgiving. Unlike chemical engines where combustion happens in controlled bursts, a nuclear reactor must withstand intense neutron flux continuously during operation. The reactor core and surrounding plumbing face constant thermal cycling as the engine throttles up or down for trajectory adjustments. This exposure causes embrittlement in metals over time, meaning the structural integrity degrades with every mission cycle. Historically, this failure mode has grounded many prototypes because standard steels become brittle enough to crack under stress when bombarded by neutrons at those temperatures. This forces us into a materials choice that pushes modern metallurgy to its absolute limit. We are talking about refractory metals like tungsten or tantalum, which can survive these conditions, but they come with their own penalties in terms of density and cost. The relationship between temperature and performance is nonlinear. While doubling the reactor temperature theoretically doubles specific impulse, practical operating temperatures hit a hard ceiling imposed by current materials science. This means we cannot simply engineer our way to infinite speed regardless of how much power we generate, because the engine components will fail structurally before reaching those theoretical extremes. The shift from chemical to nuclear propulsion fundamentally changes what engineers must prioritize during design. In traditional rocketry, the career bottleneck is combustion stability and turbopump mechanics, focusing on keeping liquid oxygen and fuel mixing perfectly without exploding in the chamber. With a fission reactor, that focus shifts entirely to nuclear materials science and thermal hydraulics. Systems architects now have to prioritize reactor containment integrity and heat exchanger efficiency over traditional metrics like thrust-to-weight ratio because a single crack in the core lining is catastrophic for the entire mission. There are competing technologies attempting to solve this problem without onboard fission, such as laser thermal propulsion, which theoretically achieves specific impulse values up to 3,000 seconds by beaming energy from Earth or orbiting mirrors. While these concepts eliminate the risk of carrying a nuclear reactor into space, they introduce their own massive infrastructure requirements and line-of-sight limitations that make them less practical for immediate human transit compared to self-contained nuclear thermal rockets, which NASA is currently developing through its DRACO program. The physics remains the same. Regardless of the power source, you need high specific impulse to reduce time in deep space. But the engineering path to get there determines whether we go or stay on Earth. The decision to pursue a nuclear path is not about chasing higher speeds for speed's sake. It is about solving the thermodynamic constraints that make human exploration impossible with current technology. We are moving from an era where chemistry limits our reach to one where physics dictates our survival, and mastering those new constraints will define whether humanity becomes a multiplanetary species or remains confined by the gravity well of its birth planet. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.